This is Unit 3E, and we're on Part 4 of our optimization problem examples. In problem 10, you have 10 feet of wire that can be cut at any point. The resulting pieces are to be bent so that one forms a square and the other forms a circle. How should the pieces be cut and used so that the maximum possible area is enclosed? And what about the minimum possible area? All right, so let's start with our 10 feet of wire here. And we're to cut it at some point. So if I cut it right there, then one of the pieces I could say is x units long, and then the other one would be 10 minus x. Right. Let's go ahead and imagine that we're going to make a circle out of this one. And I'm going to make a square out of that one. So that ultimately my goal, my objective function, is essentially to find both a maximum and a minimum value of the combined area. So let's see here. We would have as our objective function maximize and minimize the area. And I'm going to say the area of a circle would be pi r squared, plus the area of a square is length times width, but since a length and a width per square are the same, I'll just say s squared, where s is the side of the square, s times s or s squared. Typical, we've got too many variables here. So we're going to come back over here and look at how we define these and see if we can't substitute. And in this case, I think we're actually going to end up substituting for both of them. So here's where the constraints come in. We're going to use two of them this time. For the circle, I know that the piece of wire that was x units long is now all the way around here on the circumference of my circle, right? So I know that the x is equal to the circumference. And the circumference of a circle, again, you either know or you can look this up in your geometry formulas, is 2 pi times the radius, if this is my radius. Okay. So I could say the radius is actually x divided by 2 pi. That's something I could plug in right there. Now what about the square? The square I built with this piece, so I know that the whole perimeter of my square is 10 minus x, all the way around, right? If one side is s, then I can write that the perimeter of the square is 4s, and that has to equal the entire perimeter, 10 minus x. So s would be 10 minus x divided by 4, or I could rewrite that as 10 fourths is 5 halves minus a fourth x. So let's go ahead and take both of these constraints and plug them into our original area function and say my goal is to find the maximum and the minimum for this area function, which I'll now write as pi times r squared, so that would be x over 2 pi squared, plus s squared, 5 halves minus 1/4 x squared. I'm going to simplify that a little bit. Squaring that would give me x squared over 4 pi squared. And maybe I'm just going to go ahead and multiply that out. It's just a little bit easier to deal with. If I square this, I'll get 25/4 minus, the product here would be 5/8 x. And then, of course, the outers would give me another 5/8 x, negative, both of them, plus 1/16 x squared. Could have used a chain rule on the derivative instead, but I'm just choosing to multiply out this time. One of those pi's will cancel. And so my area function is, I'm going to think of this as 1 over 4 pi times x squared. Again, just thinking of how my derivative is going to look easier to do for me. Plus 25/4. That'll be a minus 10/8 x. Plus 1/16 x squared. All right, I think I'm ready for my first derivative test. A prime would be 2 over 4 pi times x to the first. Derivative there would be 0. Here I'd have a negative 10/8. And there I'd have a plus 2/16 x. I didn't simplify my fractions, but we can do that in another step. And I'd like to know where that's equal to 0. So let's see here. I'm going to take these two x pieces, and I'm going to factor out the x, and then I'm going to move the 10/8 to the other side. So it looks like that. And then I know it's a little ugly because I haven't simplified my fractions or anything, but I'm just going to turn it into a calculator problem anyway. To get x, I'll just take 10/8 and I'll divide by that sum. So there's 10/8, and I'm dividing by the sum of, let me try that again. I'm dividing by the sum of 2 over 4 pi plus 2/16. And I'm getting about 4.4 there. All right. Reminder, we wanted to find both a maximum and a minimum. So right now, the only critical value we have, 4.4, says to cut this here at 4.4. So you'd have your piece for the circle be 4.4, and your piece for the square would be 5.6, right? But that can't be both the maximum and the minimum. So we're going to need to look for another solution. The solution is going to be to look again at what is the valid closed interval that x could be a part of. And in this case, x can't be any smaller than 0, and it can't be any bigger than 10, because that would be the whole wire, right? If x is 0, we'd be using everything for the square, and if x is 10, we'd be using everything for the circle. So 0 to 10 is the closed interval on which I really want to find my max and my min. So we'll do that. We'll check out 0 and 10, as well as that 4.4 that we found for a critical value. And actually, this isn't y, this is actually my area function. So I'm going to go ahead and put the simplest area function I had, I guess, was right here. I'm going to go ahead and put that into my calculator. So 1 over 4 pi times x squared plus 25/4 minus 10/8 x plus 1/16 x squared. And we wanted to check 0, 4.4, and 10. So there we go. At 0, the area was 6.25. When x is 4.4, the area is 3.5. And for 10, we get 7.96. So it looks like the critical value that we found actually was the minimum area. The maximum area right here is what we get when we have x equal to 10, or in other words, we're using the entire wire to make a circle. So, min and max, min area, 4.4 feet for the circle, and that would leave 5.6 feet out of the 10 for the square. Maximum area, use the whole 10 feet for the circle, and we're going to have no square. All right, let's go to number 11. In number 11, we're in a movie theater with a 20-foot tall screen, the bottom of which is positioned 10 feet above the level of your eyes. How far from the screen should you position yourself so that your viewing angle of the full screen is as large as possible? One unrealistic thing here, we're going to have to assume a flat floor, which of course is not true in most movie theaters, but it's going to be in our movie theater. All right, so let's think about what this picture would look like. Here's the flat floor of the theater. And let's see, if this is the wall where the screen is, the bottom of the screen is 10 feet above the level of our eyes. And again, I'm going to have to be just slightly unrealistic here. I'm just going to go ahead and I'm going to assume that my eyes are here on the floor. I know that's a little silly, but for the purposes of this problem, that's what we're going to do. So, bottom of the screen is here 10 feet above eye level, and then it's a 20-foot screen. So this distance here for the screen would be 20. And this is our actual movie screen right here. All right. My goal is to figure out how far away I'm going to sit. So let's call that x. And what I would like to do is to have this angle, my viewing angle, theta, be a maximum. So my objective function, I would like to maximize theta, which is that viewing angle. Now, we got a little bit of work to do to write down what theta is. So I can't quite write my equation for theta yet, but we'll get there. Right? Unfortunately, theta is not part of a right triangle, and we all know that it's a lot easier to deal with trigonometry if we've got right angles. So instead of thinking about theta directly, I'm going to think of theta as the difference between two other angles. I'm going to think about this big angle here. Let me call that one alpha. And then I'll also think about this small angle here. I'm going to call that one beta. And hopefully you'll agree with me that theta is actually the big angle alpha minus the small angle beta. So that's what I'm going to write down for my objective function right now. Alpha minus beta. But we're going to definitely need some constraints in order to get this down to one variable, and probably a variable that includes the x, since that's what I'm trying to solve for. So let's see what we can do. As far as my constraints, once again, I'm going to have two of them. One for the alpha triangle and one for the beta triangle. And let's start with the alpha triangle. In this large triangle, I could see that the tangent of alpha would be 30 over x. Now you may remember that we don't love having our variable in the denominator. So maybe instead of writing it as tangent, I could write it as cotangent instead. It allows me to work with the reciprocal. And now I don't have my variable in the denominator anymore. It makes it a little easier to work with. So alpha is actually the arc cotangent of x over 30. I'll do a very similar thing for this small triangle with beta. The tangent of beta would be 10 over x. And for the same reasoning, I probably want to work with cotangent. That makes it x over 10. And so beta is the arc cotangent of x over 10. So those two equations, those two constraints, I will use to plug into my objective function. And then I'll have just the one variable x to work with, which is okay. So my goal is to maximize my viewing angle. So I want to find the maximum. And theta is alpha, so arc cotangent x over 30, minus beta, arc cotangent x over 10. All right, I'm ready for my first derivative test. The derivative of theta, and we are going to need the arc cotangent derivative, which probably isn't one that most of us have memorized, so let's grab our list of derivatives. And right here is our arc cotangent derivative, negative 1 over 1 plus x squared. Now here I don't have x, I have x over 30, so I'll have to work with that. My derivative is going to be negative 1 over 1 plus, and just like I've got the x over 30 here, I'll use the x over 30 squared down here. I also have to do a chain rule, so we'll multiply this by the derivative of that inner function, which would be 1/30. All right, similar situation over here. I'm subtracting the derivative of arc cotangent x over 10, which will be negative 1 over 1 plus, and this time x over 10 squared, times 1/10 for the chain rule. And once again, I'll just call your attention to the fact that because x over 10 was inside my parentheses here, that's what I used instead of x in the derivative. All right, I would like to know when this is equal to 0. So let's see. Simplifying a bit, I'm going to have negative 1 over 30 times 1 plus x squared over 900, minus a negative would be plus 1, over 10 times 1 plus x squared over 100 equals 0. I'm going to need a little more space here. Let's go ahead and move this term to the right-hand side. So, whoops. What's left here is going to be a positive 1 over, and I might as well distribute 10 plus x squared over 10. And then on the other side will become a positive 1. And again, I'll distribute 30 plus x squared over 30. And I'm just going to clear the fractions, multiply both sides by the common denominator, which in this case basically is just cross-multiplying. So I'll get 30 plus x squared over 30 equals 10 plus x squared over 10. And I'd still like to kind of clear my fractions, so I'm going to multiply both sides by 30. (900) plus x squared equals 300 plus 3x squared. So if I subtract the 300, I'll get 600 equals 2x squared. X squared is 300, and x would be the square root of 300, or approximately 17.3. Okay. So again, I'll let you verify this one. We would just go back to our traditional verification. And I'll let you verify that it really is a maximum. But what we're saying here is we should sit 17.3 feet away from the screen if we want to maximize the viewing angle. All right, we have one last example in this, again, rather lengthy section, I know. In example 12, we're told that two sides of an isosceles triangle are 3 inches long, and we'd like to find the angle between the two sides that will result in the isosceles triangle of maximum area. Reminder, just an isosceles triangle has two identical sides, right? So if I've got my isosceles triangle, draw it like that. Then these two sides are the same length, so let me just call them x and x for now. And I want to find the angle between the sides, theta, that's going to give me the maximum area. So my objective function, I want the maximum area. The area of a triangle in general is 1/2 the base times the height. And so I'm going to have to do a little bit of work to get there, but that's what I'm heading for. So again, I'm probably going to need two constraints. I'm going to probably have to substitute for both base and height to get my variables in here. Well, let's see what we can do. Once again, I'm going to argue that anytime you've got an angle that's not in a right triangle, it tends to be hard to work with. Much easier to work with things in a right triangle. So I'm actually going to redraw this. And I'm going to split this in half. These sides can still be x, that's fine. And I've now split my angle theta into two. Let me just for right now call these both alpha. It'll be fairly easy at the end just to double my alpha to get the theta that I want, and then I don't have to work with the fractions all the way through. All right. Let's see here. I have some height, h, and then I have some base here, b. And I should be able to use some trigonometry to write the base and the height in terms of my angle alpha. So as far as the constraints, let's see. If I think for the moment about just one of these triangles, I could say, for example, that the cosine of alpha would be h over x. And, oh, good grief. I am so sorry. I didn't read my own problem very well. They told me that the two sides are 3 inches long. I was going to say, I'm having too many variables here. I didn't include that right from the start, so let's go back and do that. This side is 3 inches. This side is 3 inches. So instead of x's here, thank goodness, I can actually have 3's. So the cosine of alpha is h over 3. That's better. And so h would be 3 cosine alpha. So that takes care of the h. I also need to deal with the b. This little piece down here now is just going to be half of b. So I could say that the sine of alpha is 1/2 b over 3. Three sine alpha is 1/2 b, and so 6 sine alpha is equal to b. So those two constraints can be used to substitute for h and b in my objective function, and then everything will be in terms of alpha. So my goal is to maximize the area, 1/2 the base, which is 6 sine alpha, times the height, which is 3 cosine alpha. Half of 18 would be 9 sine alpha cosine alpha. And there's my area function. I'm ready for my first derivative test. A prime is going to be 9 times, and it looks like I'm going to need a product rule right here. F is sine alpha, G is cosine alpha. So F prime is cosine alpha, and G prime is negative sine alpha. Product rule, FG prime will be negative sine squared alpha plus GF prime would be cosine squared alpha. And I'd like to know where that's equal to 0. Of course, I can divide out the 9, so that really just says minus sine squared alpha plus cos squared alpha equals 0. So cos squared alpha equals sine squared alpha. And that means that cosine alpha equals plus or minus sine alpha, if I take the square root on both sides. All right, if I just look at a unit circle, at pi over 4, or 45 degrees, sine and cosine are the same. And 3 pi over 4, which is 135 degrees, they're opposites. I don't want to go any further than that because then I get more than 180 degrees, which of course can't be in a triangle. So I'm going to say, based on this, alpha could be 45 degrees, or it could be 135 degrees. But I think even one of those isn't going to work, because remember, alpha was only half of the original angle theta that I'm trying to find. So this one would give me a theta of 90, and this one would give me a theta of 270, and that's too big to be in a triangle. So I think we're going to stick with 90 degrees for our theta. Okay. Once again, I would encourage you to double check that that really is a maximum using our first derivative test, that little number line test. Just for the brevity of this video, which is actually already really long, I won't show the test here. And that finally brings us to the end of 3E.